everybody, I want to go over a little bit about electron withdrawing and electron donating groups in this video. So this is a table that is from your textbook. It lays it out pretty nicely with all of the information that you really need. So this is kind of going off of the activity that we did in class the other day, where we kind of thought about why each group is ortho-para directing or meta directing, depending on the qualities of the actual substituent. So I just wanted to kind of show kind of the range that you might be seeing through this in terms of what kinds of things can be activating and what kinds of things can be deactivating. So I'm going to be going over patterns on this heavily because you know how much I love patterns. So if we look at an activating group, they all have, well, most of them have a few things in common. Probably the most obvious is probably that lone pair, right? So a lot of these, we've got some kind of atom with a lone pair. Well, let's just, oh goodness. So let's say, some kind of oxygen or nitrogen in most cases, but other things that have lone pairs can work as well. And so we have those lone pairs physically donating electron density into the benzene ring. Therefore, they are electron donating groups, right? So okay, you'll often see that shorthand as EDG. So electron donating groups, they're going to help us. They're going to help by putting electron density into the ring. That can help stabilize any kinds of carbocation intermediates that you have. It also means that the ring itself is just more nucleophilic to start with. Okay, so as we have electron density going into the ring, we can imagine a delta negative here, here, and here. If you go through those resonance structures, those are nice sites of nucleophilicity on that ring. So the more electron density we donate in, the more nucleophilic the ring becomes. So you can think about the activating or deactivating as becoming more nucleophilic. Okay, so it's activating it to be a good nucleophile, whereas deactivating is going to make it a worse nucleophile. Okay, so the other one that is not in here, but I think that it should be, is esters. Okay, so keep in mind that when you have an ester that's attached to the benzene ring, you've got that oxygen that still has a lone pair, can still donate in. The reason that these are not quite as activating as up here is because if we think about what these look like, so this is an amide, this one is an ester. Okay, so if I have my phenyl group over here, right, my benzene, let me retry that. We'll just draw little benzenes. Excuse me. Okay, so we've got our little bitty ester, little bitty amide. Okay, so the reason that they are not quite as activating for the amide and the ester as if we have the amine and the ether or the alcohol is the nitrogen lone pair or the oxygen lone pair can go into the ring, but it is also fairly tied up in the resonance with the actual carbonyl itself. So we kind of are splitting it two separate ways. So you're not getting as much electron density into either of them in this case, because we're kind of stretching it a little bit thin, but it is still going to act as an electron donating group, just not as strong of one as if you don't have resonance taking away that lone pair. Okay, so then the other one that is kind of weird is if we look at where the halogens lie, right? We've got this little dotted line here where the activating groups stop right before the halogens, but the ortho para directors go all the way through the halogens, right? So why are halogens acting as ortho para directors but don't activate the ring? Okay, so the reason for that is we're getting a kind of a clash between a resonance and an inductive effect. Okay, so if we look at an example here, let's just go with chlorine. Okay, most of the halogens are going to behave the same way, so we can just kind of generalize them. So if I have this reaction, and let's just say we're going to do a bromination, sure. Okay, so if I do that bromination, according to this table, it's going to end up orthopara. So if we look at why that is, right, we're going to have our bromine is going to form the little complex with the iron tribromide. Then we can end up attacking that electrophile with our benzene ring. They put my bromine on the para position. It's all the resonance structure will be the same in the ortho position as well. Then we can go ahead and show what kind of resonance we have going on here. Okay, so then we can get a carbocation next to the chlorine. So that chlorine does have lone pairs on it. So we can do this. Okay, it's not great. It's not a great resonance structure, but it is a resonance structure. The reason that it's not so it's not something that you see all the time, having a pi bond with a halogen, is mostly because the orbital overlap between the chlorine and the carbon is pretty poor, but you can still do it. It's just not a very strong bond. It's not like a carbon-oxygen bond. It's quite weak, but it can make kind of that double bond character. And then we can keep on going with our resonance. And we get to our final one, and then we can say, okay, well, I can't do any other resonance structures, so let's go ahead and finish off the reaction. Okay, so we're going to form HBr, make our benzene ring again. And then we get to our product, okay? You'll also form the ortho. Oops. Okay, so we're going to end up getting both the para and the ortho. So this resonance structure explains a little bit of why we see the ortho para product predominate, because there is going to be a slight amount of stability added by this resonance structure and enabling us to have another place to delocalize that positive charge. You're spreading out the charge even more, so it's going to be more stable in the end. But we still haven't addressed why it's deactivating the ring in the first place. Okay, so when we think about a halogen, we often think about them as pretty electronegative molecules, and they are, right? So they are electronegative. Oxygen is also electronegative though. So why are we seeing such a disparity? So if I have the chlorine here or the bromine, I've got a dipole going towards that chlorine, okay? So that's essentially inductively withdrawing electrons, okay? Anytime that it's induction, where it's just relying solely on the electronegativity of the atom, it's going to be weaker than if it was a resonance-based effect, okay? But if we think about oxygen versus chlorine, oxygen is falling, pretty high into our activating groups. And that's because when we do this resonance structure with oxygen, it's a really good resonance structure, right? We've got a really strong pi bond between the oxygen and the carbon. That overlap is really good. But when you start getting to the next row of elements like chlorine, like bromine, those don't have good overlap with the carbon in terms of pi bond. So this becomes a bigger impact because this is a smaller impact, okay? So we end up seeing deactivated rings but the resonance guides it to be orthopara. Okay, so that's what we're seeing when we look at halogen. So it deactivates the ring, but the presence of that even minor bit of resonance structure is going to lead us to the orthopara products. But it'll be kind of slow in a lot of cases. Alrighty. Okay, so that's dealt with that one. So the R group is the only other one that doesn't fit into those activating territory, just because it doesn't have lone pairs on it. So how exactly is it activating? How is it donating electron density? So if we think about a carbocation, okay, think about just the normal carbocation stability trend if we're only looking at substitution and not resonance, right? So we know that a primary carbocation, let's draw what those look like. A primary carbocation is less stable than a secondary carbocation is less stable than a tertiary carbocation. Okay, what stabilizes carbocations? Electrons, right? Electron density stabilizes carbocations. We think about that with resonance all the time. Like if we can push electrons towards it, that's probably going to be beneficial. So if we look at what's happening here, we're increasing the number of carbons and hydrogen atoms that are nearby. So as we increase and put on more alkyl groups, we're getting a more stable carbocation because we are donating electron density from those carbons, okay? So it's actually going to be the CH bonds or CC bonds nearby that actually serve to push electron density towards that positive charge. But think about carbocations if we're thinking about adding more substitution on it, that's going to stabilize it. Same thing on the benzene, right? It's going to do the same type of donation process. So more alkyl groups equals more stable carbocation because the alkyl groups are donating electron density. Okay, so this is again a weaker effect than resonance. So just like the induction that we talked about earlier, it is a weaker effect than resonance. but it does still make an impact, okay? And if we look at the chart, you know, it's just above, you know, it's at the bottom essentially. So it is the lowest way that you can activate, but it is still an activation. All right, on to deactivating groups. So if we look at kind of the patterns that we're looking for deactivating groups, okay, just to be clear, we're thinking about for this things that decrease the nucleophilicity of the ring. Okay, so we're thinking about things that take electron density out. So this is going to be electron withdrawing groups. Okay, often will be called EWG. So anything that could take electron density out is going to fall into that deactivating category. So if we look at just a little example here, we're automatically going to have to draw our resonance structures differently because I cannot be going that way into the benzene ring to go here, because that's going to leave my oxygen there without a full octet, which we cannot do. So we have to have the electrons moving towards that electronegative atom. So the only way to do that is by taking the electrons out of the benzene ring. And we're withdrawing from that pi system into that substituent, okay? So if we look at kind of the trend here, these are all carbonyls, okay? They are all carbonyl carbons. That are attached to the benzene ring. Okay, so that carbon, that C plus right here, that's what's doing a lot of that withdrawing power. Okay, technically nitriles are also a type of, well, they're not a carbonyl with oxygen, but they are actually carboxylic acid derivatives. So it falls into the same kind of category as the carbonyl. So if we think about that, it is still delta positive, just like a carbonyl is. The sulfur, so the sulfonate, again, same thing. We've got another delta positive atom in the middle because that sulfur is surrounded by oxygen. So it's constantly getting electron density pulled away. So it's delta plus. Our NO2, if we look at what the NO2 looks like, it straight up has a negative charge right next to it, right next to the ring. So that's a really strong electron withdrawing effect because now I've got a positive charge that all that electron density is trying to flow towards. And same thing with this one down here. We got that positive charge. When we've got the nitrogen having overloaded bonds, again, we're going to be pulling that out. Not really resonance for this like ammonium type situation, but more in terms of induction, but it's a very, very strong induction because you've got just a naked charge there. So that's kind of what we're looking for. For activating groups, we're generally going to look for lone pairs. Okay, and then for the deactivating groups, often it's going to be a carbonyl of some type, but you're looking for delta plus atoms right next to the ring. Okay, so that's kind of going to be the patterns that we're going to look for in terms of determining what's going to be a meta director, what's going to be an ortho-para director, and all that jazz. So I will be giving another video kind of demonstrating how these things work resonance-wise with all of them drawn out. So check that out. Check that one out next. Have a good one, and make sure you let me know if you have any questions.